Hello everyone, welcome to In 5 Minutes. In this video, we are going to see the next problem on higher order differential equation with variable coefficients. So this is our question. So if you see in this question, we have x plus 1 term repeating. So this equation is nothing but higher order differential equation with variable coefficients. Particularly, it is of the form of Legendre's equation. So in Legendre's equation, we put z equal to log of this term, which is x plus 1. Then our x plus 1 will be e raised to z. Then our x will be e raised to z minus 1. If we compare this equation with basic Legendre's equation, which starts with p plus q, if we compare these two terms, we get p equal to 1 and q equal to 1. And we also substitute x plus 1 into d by dx as p into d. In our case, p is 1, so it will be only d. And we substitute x plus 1 the whole square, d square upon dx square equal to p square d into d minus 1. P square is nothing but 1 square, so it will be 1 into d minus 1, which is nothing but d square minus d. So now we are going to substitute all these terms. So this whole term x plus 1 the whole square d square y by dx square will be nothing but d square minus d, plus x plus 1 d by dx will be nothing but d plus 1, and I am taking y outside, equal to 2 sine of log of x plus 1 is nothing but z. So it will be sine z. This minus d and plus d will get cancelled, and we get d square plus 1 into y equal to 2 sine z. So if you see, this equation is of the form f of d into y equal to z. So this is the linear higher order differential equation with constant coefficients. So the solution is given by y equal to yc plus yp. First we will calculate yc. So for yc, what we need an auxiliary equation. What is auxiliary equation? It is nothing but f of d equal to 0. What is f of d? F of d is this term, which is d square plus 1 equal to 0. If we take 1 on the right hand side, it will be d square equal to minus 1. So it is a square root of a negative term. So this roots of this equation will be complex. So alpha is 0 and beta is 1. In this case, when we have a complex roots, yc is given by e raised to alpha. Alpha is 0, so e raised to alpha x. But here we have variable z, so it should be e raised to alpha into z. So 0 into z into c1 cos of beta into z. Beta is 1, so c1 cos z plus c2 sine of beta z. So this is our yc. Now we will find yp. We know that general formula for yp is 1 upon f of d into z. What is f of d? F of d is nothing but d square plus 1. And what is z? Z is 2 into sine of z. I can take 2 here. We will get 2 into 1 upon d square plus 1 sine z. If you observe this equation, it is of the type 2. So in type 2, we substitute d square equal to minus of a square. What is a? A is coefficient of z in sine z term. So a is 1, so d square will be minus 1. When we substitute d square equal to minus 1, this term becomes 0, and this term is creating a problem. So when the terms create problem, we have the solution as x raised to r upon r factorial into minus 1 the whole raised to r upon 2a the whole raised to r into sine of ax plus b plus r pi by 2. So this is the solution. But in our case, we do not have x, we have z. And r is 1 and a is also 1. So now we are going to apply this formula for this part. So we get 2 into x raised to r, so z raised to r upon r factorial into minus 1 the whole raised to r upon 2a the whole raised to r. R is 1. Sine of ax plus b remain as it is, so sine of z remain as it is, plus r pi by 2. R is 1, so sine z plus pi by 2. So if we simplify this equation, we have minus 1 here, so it will be So minus 2z, and sine z plus pi by 2 is nothing but cos z, and this 2. So this 2 and this 2 will get cancelled, and we get yp as minus z cos of z. So our final solution will be y equal to yc plus yp, where yc is this term and yp is this term, and z is nothing but log of x plus 1. So this will be our final solution, and this is how we solve the problem on higher order differential equation with variable coefficients. More such problems we will see in our next video, so stay tuned for our future lectures.